Hi kids, this is probably the last video I'm going to put up. I haven't decided if I'll do one more, but this one is on solving circuits for the 4 variables that we're interested in: voltage, current, resistance, and power, and also learning about what those results mean for the circuit. Okay, so the big goal in this video is to learn how to make some predictions about what you're expecting to see in the circuit, so we can see how the observable properties of the resistors and the wires in our circuit match up with the variables and relationships that we know. So how do you know what to expect to observe in a circuit? Well, we're going to do 2 things. The first is that we're going to use sort of common sense and our own logic along with that school day analogy to make predictions about what we're going to expect to be happening at each resistor. The second thing is we're going to make what's called a VIRP table, and that is a table that lays out the voltage, current, resistance, and power values for each part of the circuit, and in a really clear way so that we can see where all the variables came from and how their values compare to other parts of the circuit. So there are a few common sense circuit rules which make sense in terms of the conservation principles we know and also in terms of the school day analogy that you should always keep in mind when you are trying to figure out what's happening with the circuit. The first is that the electrons stay in the wires, okay? They stay inside the conductors. They can't escape out of those wires or out of the resistors, and they stay in the wires that provide a route back to the battery. No electrons are used up or gained in the circuit. And this is something that a lot of kids, I think, come into physics thinking that electricity means we're using up electrons. But the principles of conservation of mass and charge tell us we can't create or destroy electrons. So we're not using up the electrons. What we're using up is the energy. But what that means functionally is that the same amount of current, which is electrons per second, that comes out of the battery has to go back in the other side of the battery. We can't gain or lose any current throughout the circuit because otherwise we'd be violating those conservation principles. As far as a school day goes, this means that the same number of kids that leave the house have to come home at night. Okay, we're not going to gain any extra kids during the school day, and we're not going to lose any kids either. So it works in that analogy as well. The second common sense rule is that the total energy used up every second in the resistors is exactly equal to the total energy produced by the battery every second. This is a manifestation of conservation of energy. So what this means is that those electrons get their energy at the battery, and if the electrons get 20 joules of energy every second from the battery, that means somewhere in the circuit those electrons are using up every bit of that energy. So they're using 20 joules every second at the resistors, so that when they return to the battery they have none. Okay, you got to spend all your money, spend all your energy before you come back home. This analogy makes sense to you because you start off your day with no energy when you wake up in the morning, and then you slowly over the course of the day burn off that food that you ate for breakfast, and then by the time the next morning rolls around you're really hungry, you don't have any energy again. So that's kind of the same idea as this rule. So the most simple case would be a single resistor circuit. This would be a circuit that has just a single battery in it with some wire connecting it to a bulb in a complete circuit. You'll notice that we connect to both ends of the battery here. And if we want to kind of be able to describe in mathematical terms what's happening in this light bulb, we're going to make this VIRP table below to help us lay out the values of those variables. So V is voltage, I is current, R is resistance, and P is power. So you're going to set up your table like this, and every resistor in the circuit should get its own column. If there's more than one, you'll add a column for the total, which is kind of like what's happening at the battery, but since we only have one resistor here, it's pretty straightforward. It's the only place that energy is going to be able to be used up in the circuit, so we only need one column. And you'll start by putting in the values that are set by the components. So first I'll look at my battery and I'll see what voltage it has. In this case, I have a 12-volt battery, so I'm going to put in 12 as the voltage for the bulb, because however much energy every second, however much energy each electron is getting at that battery, the only place it has to use that energy is in the light bulb, right? If this was a school day, you got 12 energies in the morning from your house. You're only taking one test because you're going through one bulb. You might as well use all 12 of those energies in that single bulb. The second thing you should know from the beginning is the resistance of the bulb. You can measure this using a multimeter, which we'll show you how to use in class. But let's just say we pulled out our probe, we measured the bulb, and it said 2 ohms. As soon as you have two variables in a column that you know the value for, so this column, this bulb column here, we know that we have the voltage and the resistance, we can now use our two equations to calculate the other variables. So we have an equation, I equals V over R. So if I is equal to 12 volts divided by 2 ohms, that should give us a current of 6 amps. So we can predict that based on that voltage and that resistance for this circuit, there's going to be 6 electrons every second that leave the battery. 6 electrons every second are pushed through that light bulb. 6 electrons every second are returning to the battery, because we can't gain or lose electrons, just like you can't gain or lose students in a school day. The power is equal to the voltage times the current. So we've got 6 electrons moving every second. Each electron has 12 joules of energy, or 12 volts. That means every second, 72 joules of energy get dumped into the light bulb, okay? Right, 6 times 12. It's the number of electrons times the amount of energy each electron has. That tells me how much power is going into that light bulb and available to be converted into other things like light and heat. So we're going to move up in complexity a little bit from single resistor circuits into circuits that have multiple resistors. There are fundamentally two different ways of hooking up more than one resistor in a circuit. The first way is known as a series circuit. Of course, you know the word series means to do something one at a time, back to back to back to back, like a series of books or a series of movies or the World Series. And that's how it is in resistors in a series circuit. So in that drawing on the left, you'll notice there are 2 light bulbs. In order to get back to the batteries, the electrons have to go through both of those in turn, so one after the other. The circuit diagram on the right shows a battery. Looks a little different, don't worry about it, but the electrons leaving that battery actually have to go through 4 resistors. So you can put as many resistors in a series circuit as you want. So what kind of conceptual things can we say about how a series circuit is different than a circuit with just a single resistor in it? Well, as I mentioned a minute ago, the electrons have to go through all the resistors before returning to the battery. What this means in terms of calculating values in the circuit is that there's the same current through each bulb, because if 4 electrons every second get pushed out of the battery, that means 4 electrons every second are getting shoved through the first light bulb, 4 electrons every second are getting shoved through the second light bulb, and 4 electrons every second are going back to the other side of the battery. In order to keep conservation of mass, etc., that has to be true. The second thing that we can say about series circuits is that the electrons that leave the battery with some energy, they're going to use some of their energy in each bulb. Okay, this would be like a school day where you're taking 2 tests. It doesn't make any sense to use up all your energy on the first test and fail the second test. It also doesn't make any sense to try to skate through the first test without using energy and save it all for the last test. So it doesn't matter where the light bulbs are. It doesn't matter how close they are to the battery. Those electrons are going to save up their energy and split it around to all the light bulbs in the circuit. Now, they don't necessarily split that energy evenly. Just like you would in a school day, the electrons are going to spend more energy or use more voltage on the higher resistors, on the more difficult test, if you will. So when electrons pass through multiple light bulbs in series, they do save some of their energy for each resistor, but they're going to use most of their energy or more of their energy on the harder resistors. The other kind of circuit is known as a parallel circuit, and if you look at those drawings, you'll see how this circuit is different. Instead of the electrons being forced to go through both of the bulbs in the circuit, the electrons actually have a choice. They can either go through the top bulb and go straight back to the battery, or they could go through the bottom bulb and go straight back to the battery. Now, of course, you could imagine some crazy path where those electrons did some figure 8 or something and went through both light bulbs, but electrons are pretty logical little guys. You know, if they go through one light bulb and they see a path back to that positive side of the battery, there's no way they're going to choose to go through another light bulb just for the sake of doing it. So once you get through a light bulb, and if you see that path back to the battery, you're just going to take it. just like you probably wouldn't choose to take a second test if you didn't have to, if you could go home without taking it. You'll notice the same thing in the circuit diagram on the right. We got a battery down there in the middle, and there's a split. Okay, the electrons leave the battery. There's a junction where they can choose one of those three paths. Now, it looks like that middle path is the shortest path, but I'm going to remind you that electrons don't care at all about the length of the wire that they're traveling through. So the shape of the paths, the length of the wire doesn't make any difference in the path that the electrons choose. Now there is something that does make a difference about which path the electrons are going to choose. Obviously, the electrons would choose, most of the electrons are going to choose to take an easier test if they have a choice. So if R1 and R2 and R3 have different resistances, what you'll find is that the current splits. There's going to be some current through each, so some electrons will choose every path. They don't all go through the easier path, but more of the electrons are going to choose to go through the easier path, just like if you had a choice between three tests, a physics test, English test, and a, I don't know, basket weaving class. I shouldn't say that because basket weaving is pretty hard for me, but at any rate, you know, more students would probably choose to take the easier test, but there might be some kids that would choose to take physics, and some kids that would rather do English. So all three of those paths are going to get some electrons, but more go to the easier one. As far as the voltage goes, since each electron is only going through one resistor, so they get all their energy, they have to go through one resistor, and then they can go straight back to the battery. That electron is going to use up all of its energy in that one resistor, so it doesn't have to share it because it's only going through one resistor. So we're going to make a VIRP table with the series circuit and talk a little bit about why all the values in this table make sense. So here's a series circuit. You'll notice the resistors are back to back, and I've given those resistors values so we can plug it into our table. The table in this case is going to be a little bit more complicated. There will be three columns, one for R1, which is my first resistor, one for R2, which is my second resistor, and then another column that is going to be the total voltage, current, resistance, and power values for the whole circuit. You can also think of this as what's happening basically at the battery. So filling out this table is sort of a Sudoku puzzle. We've done those in the past where you first put in the obvious values that you know, and then you start with your logic and with your equations figuring out the other values in the circuit. So I usually start by putting in my two resistors because I can read them right off of there, and the voltage is going to be the total voltage because that's the total amount of energy that each electron is going to get is 12 volts. What we're really trying to do here is get two values in a single column, because if we can do that, then we can use our equations. But we don't have that yet. We only have one value in each column. So you've got to kind of think logically about this circuit. And what I start to think about is, if this was a school day and I had to take two tests back to back, would the total resistance in that circuit be more or less than just taking one test? And it should be logical that it's more. How much more? Well, if I have to take a test level 1 and another test level 2, it should make logical sense that the total difficulty of the day is level 3. So you can, in a series circuit where you have to take both tests, you can assume that the total resistance is going to be the sum of the individual resistances. Now that we have two values in that total column, we can go ahead and calculate I. I is equal to V over R, so 12 over 3, which gives me 4 amps. And power is going to be equal to I times V, so 48 watts. All right, now we got to do a little bit of physics because we've got one column done, but we still don't have two values in the other column. So we need to think about what we understand and know about series circuits. If you think back to the last slide, you'll remember that the current is the same through each of those resistors because there's only one path for those electrons to take. So we can't gain or lose electrons. That means however many resistors are coming out of the battery, which is 4 amps, must also be going through the first resistor and must also be going through the second resistor and coming back to the battery. So we can fill out all of my current values because in a series circuit, the current has to be the same everywhere in the circuit. Now that we've got two values, we can use our equations. I equals V over R, so 4 equals unknown voltage divided by 1, which means that R1 is going to be 4 volts. And for R2, in that column, it's going to be 4 equals some unknown value divided by 2, which is 8 volts. So there's actually more voltage being used up in that second resistor, which should make sense if you think about that as a harder test. You can also calculate the power. So 16 watts is 4 times 4 in the first resistor, and 32 watts is 4 times 8 in the second resistor. So let's look at each of those rows one at a time and just talk briefly about why it makes sense. The voltage row makes sense because, as we mentioned earlier, we've got to use up the 12 joules of energy we have. So the total is going to be 12. We have to add up to 12, which we do, 4 and 8. And you notice that the electrons use a higher percent of their energy in the more difficult resistor. Specifically, if that resistor is twice as large, so 2 versus 1, we're going to use twice as much energy, twice as much voltage in that resistor as well. The current makes sense because, as we mentioned before, there's the same number of electrons moving through each location in the circuit every second. This is conservation of mass and charge. The resistance values all make sense because the total circuit has more resistance than the individual resistors, because each electron has to go through more than one resistor. So it's a tough school day. And the power makes sense because more power is used up at the larger resistor. And the reason why we notice that is because even though the same number of electrons are going through each resistor, each electron is dumping more of its energy in that big resistor. So that means there's more power there. If these were light bulbs, that would be a brighter bulb. If these were toasters, that would be a better toaster. But the one thing that is always true on every circuit you do, whether it's series or parallel, is that the total power is going to always equal the sum of the individual powers. This is a conservation of energy at its finest. We have to have the total energy being produced by the battery every second used up in the circuit, every second. Okay, so let's see what it looks like to make a VIRP table for a parallel circuit. You'll see a circuit diagram there with a 12-volt battery and 2 resistors in parallel, a 2 ohm resistor and a 1 ohm resistor. When you make your VIRP table, you're going to have 3 columns, one for each resistor and also one for the total values for the whole circuit. The first things I would put in there are the values straight from the circuit diagram. So I'll put in resistor 1 value and resistor 2 value and a total voltage value for the circuit. Now, a quick caution here. On the series circuit, the next thing we did is jump right ahead and put in our total resistance. And that made sense because in a series circuit, the electrons have to go through both resistors. So it makes sense that the school day or the circuit has more resistance than the individual resistors do on their own. But in this kind of circuit, each electron is only going through one or the other resistor. So it wouldn't make sense that this is a particularly hard circuit to get through. You've got a choice. At minimum, you're going through the 1 ohm resistor. So there's no reason why the total resistance in the circuit would be 3. So we can't actually do that from the start. Instead, we need to think about what's happening with voltage. Remember that voltage is the amount of energy each electron gets. So when the electrons leave the battery, every single electron has 12 joules of energy. Now, those electrons have to use up all the energy before they come back, and they're only going through one resistor, which means that if they go through the resistor number 1, they're going to have to use all 12 joules of energy. If they go through resistor 2, they're also going to use 12 joules of energy. They're different electrons, but no matter which path they take, they have to use up all of their energy. So that means the voltage values for each of those resistors should be 12 volts. So now we have 2 values in the R1 and the R2 column, which means we can use our 2 equations, I equals V over R and P equals IV, to calculate the missing P values in those columns. So I is 12 over 2, which is 6. For R2, we're going to have 12 over 1, which is 12. So we have 6 amps going through the first resistor and 12 amps going through the second. And we can calculate our power values as well. So the very last thing we're going to do in this case now is get into our total. If you remember that charge is conserved, or mass is conserved, the next realization that you should come to is that if 6 electrons every second are going through resistor 1 and 12 are going through resistor 2, that means the battery had to be spitting out 18 electrons every second to make this happen. And those electrons will then come back together again after they go through the resistors, and they'll go back in the other side of the battery. So the next step is sort of a conservation of charge step, figure out what the total current in the circuit is going to be. And then from there, we have the equations again to calculate R and P. So we'll use our first equation, I equals V over R, to solve for R. We should get 0.7 ohms. And then when you do power, it's going to be P equals I times V, or 216 watts. Whenever you complete a VIRP table, it's really important that you go through each row and think about whether the values make sense. So in this circuit, the voltage values make sense because since each electron will only go through one resistor or one path, they're going to dump all of their energy in that resistor, which means the resistance is the same through each path. The current values make sense because two reasons. First thing, we noticed that charge is conserved. The total charge per second that's going through the individual resistors is the same as the total in the circuit. So 6 plus 12 is 18. The other thing that you may have noticed about this is that more electrons were going through R2, okay? And that's interesting because that's the easier resistor or the easier test. And that should make sense from our school day analogy. If you had a choice between a hard test or an easy test, most of the kids or more kids are going to choose the easy test than choose the hard test. The resistance row is the one that kids struggle with the most in this kind of circuit, because when you look at the total, which is 0.7 ohms, that seems like a really weird value. The easiest way I can describe this is like trying to get into a room that has two doors. Okay, trying to shove a whole bunch of kids in through the cafeteria door, but there's two doors instead of one. So it's actually easier to get through the circuit the more paths there are, which means that the total resistance in a parallel circuit is actually always very low. It's even lower than the individual resistor values in the circuit. So whenever you do this, you're always going to get a number that is less than the lowest resistance. So in this case, 0.7 ohms makes sense. And the last thing is power, which is the most important variable, of course. We noticed that, again, power is conserved, which it will be in every VIRP table you ever make. So R1 plus R2 is equal to total. That's a conservation of energy situation there. But the other thing you should notice is that in this circuit, R2 is actually the brighter bulb. It's spitting out 144 joules of energy every second, where R1 is only spitting out 72 joules of energy every second. And that's important because in the series circuit, it was actually the higher resistance bulb that was more, that used more power. Because in the series circuit, it was getting more voltage. In this circuit, they get the same voltage, but the lower resistance bulb gets more current, which means more electrons go through that path, so it's actually brighter. Okay, so the last slide in the show is going to be a comparison between series and parallel circuits. As we mentioned when we went through the VIRP tables, the bulb with more resistance is brighter in series because the current is the same for both, which means the more voltage it has, the more power it gets. Compare and contrast to a parallel circuit where it's actually the lower resistor bulb is brighter because they have the same voltage, which means that the bulb that has the more current is going to have more power. Another comparison is that in a series circuit, there's more overall resistance because we keep adding up those resistors, and that means ultimately that there's less current in the circuit and less power in the whole circuit. So a series circuit is dimmer in general. And in a parallel circuit, it's the reverse. There's less overall resistance, so we get more overall current and more power. And one thing that you maybe hadn't thought of is that in a series circuit, if you put a single switch anywhere in the circuit, you're going to be turning on and off all of the resistors. Whereas in parallel, you could actually have individual switches for each bulb. The reason I highlight some of these things is because I want you guys to think about which of these circuits is more useful for specific applications in your life. Okay, we made it. So let's review the essential question. How can I organize my data and use equations to predict the behavior of more complicated circuits? So using that VIRP table and thinking about how all the results make sense and relate to each other is the tool that you'll be using to try to predict what's happening inside of a circuit. Thanks for your time.